Amine corrosion as a part of uniform or localized loss in thickness phenomena. Description of amine corrosion based on API 571, number A. Amine corrosion refers to the general and/or localized corrosion that occurs principally on carbon steel in amine treating processes. Corrosion is not caused by the amine itself, but results from dissolved acid gases, CO2 and H2S, amine degradation products, heat-stable amine salts, SAS, and other contaminants. Number B. Stress corrosion cracking of carbon steel in amine services. Here's a detailed description of amine corrosion, focusing on its nature as a form of general and localized corrosion. Introduction. Amine corrosion refers to the degradation of metal materials, particularly carbon steel and other alloys, caused by exposure to amine-based solutions. These solutions are widely used in the oil and gas industry for gas treatment processes, such as removing hydrogen sulfide, H2S, and carbon dioxide, CO2, from raw natural gases and other fluids. While amines are effective for gas sweetening, their interaction with metal surfaces can lead to various forms of corrosion, which can compromise equipment integrity and safety. Types of amine corrosion. Amine corrosion can manifest as either general or uniform corrosion or localized corrosion. Let's go through the. Number 1 is general or uniform corrosion. This form involves a relatively even and widespread removal of metal across the surface exposed to the amine solution. The mechanism of general or uniform corrosion is, it occurs when the entire metal surface is uniformly exposed to corrosive agents, leading to a consistent attack. The characteristics general or uniform corrosion includes smooth, even thinning of the metal, predictable corrosion rates, which can be estimated and monitored, usually easier to detect and manage through routine maintenance. Types of amine corrosion. Number 2 is localized corrosion. This corrosion affects specific areas of the metal surface, leading to pitting, crevice corrosion, or stress corrosion cracking. The mechanism of localized corrosion is, localized attack occurs due to differences in local chemistry, such as areas with differential oxygen concentration, crevices, or deposits that create microenvironments conducive to corrosion. The characteristics localized corrosion includes formation of pits or cavities that penetrate deep into the metal, rapid material loss in specific areas, difficult to detect early, potentially leading to catastrophic failure if untreated. Mechanisms of amine corrosion includes, the first is chemical interaction. Amines react with CO2 and H2S, forming corrosive intermediate compounds like carbamates and amine salts that can lower pH locally. The second is hydrogen embrittlement. The formation of hydrogen sulfide and other reactive species can lead to hydrogen absorption into the metal, causing embrittlement. The third is deposition and scale formation. In some cases, corrosion products or impurities deposit on the metal surface, creating crevices that promote localized attack. And the fourth is pH fluctuations. The interaction between amines and acidic gases can cause local pH drops, intensifying corrosion at specific spots. Factors influencing amine corrosion includes, the first is amine type and concentration. Different amines, MEA, DEA, MDA, etc., have varying corrosive potentials. The second is temperature. Elevated temperatures accelerate corrosion processes. The third is presence of impurities, oxygen, carbon dioxide, hydrogen sulfide, and other impurities increase corrosion risk. The fourth is flow rate. Turbulent flow can remove protective films and expose fresh metal surfaces. And the fifth is material composition. Certain alloys and coatings are more resistant to amine corrosion. Consequences of amine corrosion includes, the first is equipment failure due to thinning or pitting. The second is increased maintenance costs. The third is potential safety hazards from leaks or catastrophic failures. And the fourth is contamination of the processed gases. Mitigation strategies for amine corrosion can be considered, includes use of corrosion-resistant materials or coatings, proper control of amine concentration and temperature, regular inspection and monitoring for early detection, addition of corrosion inhibitors, and maintaining optimal flow and avoiding stagnant conditions. Amine corrosion is a complex phenomenon that can occur as either uniform or localized attack, depending on operating conditions and material factors. Understanding the detailed mechanisms and contributing factors is essential for designing effective mitigation strategies to ensure the longevity and safety of amine treatment systems. Amine corrosion affected materials based on API 571, primarily carbon steel. 300 series SS are highly resistant. Here's a detailed explanation of the materials affected by amine corrosion, focusing on how both general and localized corrosion impact different materials. Introduction: Amine corrosion primarily targets metallic materials used in gas treatment plants and pipelines, where amine solutions are employed to remove acidic gases like CO2 and H2S. The susceptibility of various materials to amine corrosion depends on their chemical composition, microstructure, and environmental conditions. Both general, uniform, and localized corrosion can affect these materials differently, leading to structural degradation and potential failure. Common materials affected by amine corrosion includes: number 1 is carbon steels. It is the most widely used material in gas treatment and processing due to its cost-effectiveness and mechanical properties. The vulnerability of carbon steel are: for general corrosion, carbon steel is highly susceptible to uniform thinning when exposed to amine solutions containing corrosive agents like H2S and CO2, especially at elevated temperatures. And for localized corrosion, pitting and crevice corrosion can occur in areas where protective films are damaged or where deposits end. Microcrevices concentrate corrosive agents. The impact of carbon steel are: thinning of walls, pitting that can lead to leaks or catastrophic rupture. Common materials affected by amine corrosion. Number 2 is low alloy steels. These steels contain small amounts of alloying elements, such as chromium, nickel, to improve corrosion resistance. The vulnerability of low alloy steel are, generally, more resistant than carbon steel but can still suffer from localized attack under aggressive conditions. Pitting and crevice corrosion are possible if the alloying elements do not form a stable passive film in the amine environment. And the impacts of low alloy steels is: localized damage in crevices or areas with deposit. Buildup. Common materials affected by amine corrosion. Number 3 is stainless steels, for example, 304, 316, 317. Stainless steels contain chromium and other alloying elements that promote the formation of a passive oxide layer, providing corrosion resistance. The vulnerability of stainless steels are: general corrosion, generally resistant under mild conditions; localized corrosion, susceptible to pitting and crevice corrosion in the presence of chlorides, H2S, or other aggressive species in amine systems, especially at high temperatures. And the impacts of stainless steels is: pitting holes and crevices form, especially in areas with deposits or restricted flow. Common materials affected by amine corrosion. Number 4 is nickel alloys, for examples, Inconel, Monel. These are high-performance materials used in highly corrosive environments due to their excellent corrosion resistance. The vulnerability of nickel alloys are, generally, resistant to both uniform and localized corrosion. However, under certain conditions, such as high H2S concentrations, high temperatures, even these alloys can suffer localized attack. And the impacts of nickel alloys is: if corrosion occurs, it can lead to pitting or stress corrosion cracking. Common materials affected by amine corrosion. Number 5 is coatings and linings. Protective coatings, for examples rubber linings, epoxy paints, ceramic linings, are applied to shield vulnerable substrates. The vulnerability of coatings and linings are: damage to coatings can expose underlying metal to localized corrosion. In some cases, coatings can degrade over time under chemical attack, and the impacts of coatings and linings is: accelerated localized corrosion if coatings are compromised. Factors influencing material susceptibility to amine corrosion includes: the first is chemical composition. Materials with passive films, stainless steels, nickel alloys, are more resistant but not immune. The second is temperature. Elevated temperatures can weaken passive films and accelerate corrosion. The third is presence of chlorides and impurities. Chlorides promote pitting and crevice corrosion, especially in stainless steels. The fourth is flow conditions. Turbulence can erode protective films, exposing fresh metal. And the fifth is system design. Areas with crevices, deposits, or stagnant zones are more prone to localized attack. These are the summary of the materials most commonly affected by amine corrosion include, the first is, carbon steel, highly susceptible to both uniform and localized corrosion. The second is, low alloy steels, moderate susceptibility, localized attack possible. The third is, stainless steels, generally resistant but vulnerable to pitting and crevice corrosion under certain conditions. The fourth is, nickel alloys. Excellent resistance but not entirely immune under extreme environments. And the fifth is, coatings and linings, protect underlying materials but can be compromised, leading to localized corrosion. By understanding the specific material susceptibility, it helps in selecting appropriate materials and implementing effective corrosion control measures to ensure safe and reliable operation of amine systems. Amine corrosion critical factors based on API 571, Number A. Corrosion depends on design and operating practices, the type of amine concentration, contaminants, temperature and velocity. Number B. Amine corrosion is very closely tied to the operation of the unit. With a few exceptions, carbon steel is suitable for most components in a properly designed and operated unit. Most problems can be traced to faulty design, poor operating practices or solution contamination. Number C. Corrosion is also dependent on the type of amine used. In general, alkanolamine systems can be rated in order of aggressiveness from most to least as follows: monoethanolamine (MEA), diglycolamine (DGA), disopropylamine (DIPA), diethanolamine (DEA), and methyldimine (MDA). Critical factors. Number D. Lean amine solutions are generally not corrosive because they have either low conductivity and/or high pH. However, an excessive accumulation of heat-stable amine salts, SAS, above about 2%, depending on the amine, can significantly increase corrosion rates. Number E. Lean amine solutions contain a small amount of H2S which helps to maintain a stable iron sulfide film. Overstripped lean solutions can be corrosive if there is inadequate H2S present to maintain the protective iron sulfide film. Number F. Ammonia, H2S and HCN accelerate corrosion in the regenerator overhead condenser and outlet piping as well as reflux piping, valves and pumps. Critical factors. Number G. Corrosion rates increase with increasing temperature, particularly in rich amine service. Temperatures above about 220 degrees Fahrenheit 104 degrees Celsius can result in acid-gas flashing and severe localized corrosion due to two-phase flow, if the pressure drop is high enough. And number H. Process stream velocity will influence the amine corrosion rate and nature of attack. Corrosion is generally uniform, however high velocities and turbulence will cause localized thickness losses. For carbon steel, common velocity limits are generally limited to 3 to 6 frames per second for rich amine and about 20 frames per second for lean amine. Here's a detailed explanation of the critical factors that influence amine corrosion, applicable to both general and localized corrosion. Introduction. Amine corrosion in gas treatment systems is governed by several interrelated factors that determine the severity and type, general or localized, of corrosion. Understanding these critical factors is essential for designing effective mitigation strategies, selecting appropriate materials, and ensuring safe, reliable operation. Critical factors influencing amine corrosion includes: Number 1 is chemical composition of the amine solution, type of amine solution. Different amines such as MEA, DEA, MDEA have varying corrosive potentials. For example, MEA tends to be more aggressive than MDEA. Amine concentration. Higher concentrations increase the capacity for acid absorption but also elevate corrosivity, especially if the solution becomes saturated with corrosive species. Amine impurities. Presence of contaminants such as oxygen, chlorides, and iron salts can significantly accelerate corrosion, especially localized attack. Critical factors influencing amine corrosion. Number 2 is presence of acidic gases, H2S and CO2. H2S concentration. Hydrogen sulfide is highly corrosive, especially in the presence of moisture, leading to sulfide corrosion and hydrogen embrittlement. CO2 levels. Carbon dioxide reacts with amines to form carbonic acid, lowering pH and promoting corrosion. Synergistic effects. The combined presence of H2S and CO2 can intensify corrosion rates. Critical factors influencing amine corrosion. Number 3 is temperature. Elevated temperatures increase chemical reaction rates, reducing the stability of protective oxide films and promoting faster corrosion. Critical temperature range: above certain thresholds, the risk of localized corrosion, pitting, crevice, increases due to destabilization of passive layers. Critical factors influencing amine corrosion. Number 4 is pH and local acidification. Acidic conditions, formation of corrosive species, like carbonic acid or H2S, lowers pH, making the environment more aggressive. Localized acidification, microenvironments within crevices or deposits can become significantly more acidic than bulk solution, leading to localized corrosion. Critical factors influencing amine corrosion. Number 5 is presence of oxygen and other contaminants. The presence of oxygen promotes oxidation and can break down protective oxide films, increasing corrosion susceptibility. The presence of chlorides and halide, chloride ions are notorious for promoting pitting and crevice corrosion, especially in stainless steels. Critical factors influencing amine corrosion. Number 6 is flow dynamics and hydrodynamics. Flow rate: high flow can erode protective films, exposing metal to corrosive agents. Erosion corrosion. Stagnant zones: areas with low flow or stagnant conditions promote deposit formation and localized corrosion. Turbulence can cause mechanical wear and remove protective films, exacerbating corrosion. Critical factors influencing amine corrosion. Number 7 is system design and material compatibility. Design aspects: sharp corners, crevices, weld zones, and deposits can serve as initiation sites for localized corrosion. Material selection: use of incompatible materials increases vulnerability. Materials with poor resistance to H2S, chlorides, or high temperatures are more prone. Critical factors influencing amine corrosion. Number 8 is presence of deposits and microenvironments. The presence of deposits, scale, dirt, or corrosion products can create crevices that trap corrosive agents, leading to localized attack. The presence of microenvironment conditions, variations in pH, oxygen, and ion concentration within deposits can accelerate localized corrosion. Critical factors influencing amine corrosion. Number 9 is inhibitors and protective coatings. Corrosion inhibitors: effectiveness depends on proper concentration and compatibility with amine systems. Coatings and linings protect materials but may degrade over time, exposing the metal to localized attack. In essence, controlling these critical factors by optimizing operating conditions, selecting suitable materials, and implementing protective strategies is vital to minimizing both uniform and localized amine corrosion. Amine corrosion affected units or equipment based on API 571. Number A, amine units are used in refineries to remove H2S, CO2 and mercaptans from process streams originating in many units including the crude, coker, FCC, hydrogen reforming, hydroprocessing, and tail gas units. Number B, the regenerator reboiler and the regenerator are areas where the temperature and turbulence of the amine stream are the highest and can cause significant corrosion problems. Number C, the rich amine side of the lean/rich exchangers, hot lean amine piping, hot rich amine piping, the amine solution pumps, and the reclaimers are also areas where corrosion problems occur. Here's a comprehensive and detailed explanation of the units and equipment affected by amine corrosion, considering both general, uniform, and localized corrosion. Introduction: amine corrosion can compromise various components within gas treatment and amine systems. The extent and nature of damage depend on factors like material selection, operating conditions, and system design. Both general corrosion, uniform thinning, and localized corrosion, pitting, crevice corrosion, can lead to equipment failure, safety hazards, and operational inefficiencies. Affected units and equipment by amine corrosion includes: number 1 is absorber columns, amine contact towers. The function of absorber columns is to remove acid gases, CO2, H2S, from gases via contact with amine solutions. Vulnerable areas of absorber columns includes inner surfaces of tower wall and shell, continuous exposure to corrosive amine solutions, especially at high temperatures, tray and packing supports, microenvironments where deposits form, promoting localized attack. Nozzles and flanges, points of mechanical stress and potential corrosion initiation. Corrosion modes commonly occurs on absorber columns, includes general, thinning of the metal wall, localized, pitting or crevice corrosion around nozzles, supports, or deposit buildup zones. Affected units and equipment by Amine corrosion. Number 2 is Amine regenerators, stripper columns. The function of stripper columns is to regenerate amines by stripping absorbed gases. Vulnerable areas of stripper columns includes column internals, trays, packing, and support structures, heaters and reboilers, heat exchange surfaces exposed to corrosive amine vapors, reflux lines and drums, areas with potential for deposit formation and corrosion. Corrosion modes commonly occurs on Amine regenerators, stripper columns, includes, similar to absorbers, with the added risk of localized corrosion at welds, supports, or areas with thermal stress. Affected units and equipment by Amine corrosion. Number 3 is pumps and compressors. The function of pumps and compressors is to circulate and compress amine solutions and gases. Vulnerable areas of pumps and compressors included impellers, casings, and seals, exposed to corrosive amine solutions, especially during startup or shutdown. Corrosion modes commonly occurs on pumps and compressors, includes general corrosion leading to material thinning, localized corrosion, pitting, around seals or welds due to microenvironmental differences. Affected units and equipment by Amine corrosion. Number 4 is heat exchangers. The function of heat exchangers is to transfer heat between process streams. Vulnerable areas of heat exchangers included tube sheets and tubes, direct contact with corrosive amine solutions, shell and tube internals, areas with potential for deposit accumulation and localized attack. Corrosion modes commonly occurs on heat exchangers, includes uniform thinning of tubes, pitting or crevice corrosion at tube joints, welds, or areas with deposits. Affected units and equipment by Amine corrosion. Number 5 is storage tanks, amine solutions and waste. The function of storage tanks is to transfer heat between process streams. Vulnerable areas of storage tanks included tank walls and bottoms, continuous contact with corrosive liquids, nozzles and flanges, entry/exit points susceptible to localized attack. Corrosion modes commonly occurs on storage tanks, includes general corrosion causing wall thinning, localized corrosion at welds, or areas with sediment buildup. Affected units and equipment by Amine corrosion. Number 6 is piping systems. The function of piping systems is to transport amine solutions and process gases. Vulnerable areas of piping systems included long runs, bends, and fittings, sites where deposits or stagnation can occur, supports and hangers, areas with potential for crevice formation. Corrosion modes commonly occurs on piping systems, includes uniform corrosion in flowing conditions, localized pitting and crevice corrosion in stagnant or deposit-laden zones. Affected units and equipment by Amine corrosion. Number 7 is valves and fittings. The function of valves and fittings is to control flow within the amine system. Vulnerable areas of valves and fittings included seats, gaskets, and seals, microenvironments promoting crevice corrosion, welded joints, sites prone to localized attack if weld quality is poor. Corrosion modes commonly occurs on valves and fittings, includes localized corrosion leading to leaks or failures. Affected units and equipment by Amine corrosion. Number 8 is dehydration and filtration units. The function of dehydration and filtration units is to remove water and impurities from amine solutions. Vulnerable areas dehydration and filtration units included filter housings and piping, potential for deposit buildup. Corrosion modes commonly occurs on dehydration and filtration units, included localized attack at welds or areas with deposits. Affected units and equipment by Amine corrosion. Number 9 is other equipment such as scrubbers, reactors, and gas contact equipment, similar vulnerabilities due to exposure to corrosive gases and liquids. Localized corrosion often occurs at specific vulnerable points like welds, supports, deposits, crevices, or areas with microenvironmental changes. General corrosion results in uniform thinning of the equipment walls, which can lead to sudden failures if not detected early. Effective corrosion management involves regular inspection, material selection, protective coatings, and operational controls to minimize exposure to corrosive conditions. Amine corrosion appearance or morphology of damage based on API 571, number A, carbon steel and low alloy steels suffer general uniform thinning, localized corrosion or localized under deposit attack, see Figure 5.1, localized amine corrosion at the weld found in piping from reboiler to regenerator tower in an MEA unit. Many other similar cases found, some going as deep as half thickness. They were originally found and mistaken as cracks with shear wave UT inspection. See Figure 5.2, hot lean amine corrosion of carbon steel. See Figure 5.3, preferential weld corrosion in lean amine. See Figure 5.4, preferential corrosion in amine regenerator reboiler return elbow. See Figure 5.5, corroded reboiler exchanger shell near liquid level from an amine regeneration unit. Numbers drawn on figure are UT thicknesses in inches. Nominal wall 0.550 inch. See Figure 5.6, corroded amine regenerator column shell near a downcomer. Numbers drawn on figure are UT thicknesses in inches. Nominal wall 0.500 inch. Number B, thinning will be uniform in nature when the process stream velocity is low, while it will be localized for high velocities associated with turbulence. Here's a detailed explanation of the appearance or morphology of amine corrosion, covering both general, uniform, and localized corrosion. Introduction. The physical manifestation or morphology of corrosion provides critical clues about the underlying corrosion mechanisms, severity, and affected areas. In amine systems, corrosion can manifest in various forms, ranging from uniform thinning of metals to highly localized attacks such as pitting or crevice corrosion. Appearance and morphology of amine corrosion includes, number 1 is general or uniform corrosion morphology. Description: uniform thinning of the metal surface across large areas, typically appears as a smooth, matte, or dull surface with a consistent loss of material. Visual features of general or uniform corrosion includes surface texture. The surface becomes rougher and duller due to oxide or corrosion product buildup. Color changes, may develop rust-colored, iron oxide, brown, or black corrosion products depending on the metal and environment. Thickness loss, measurable reduction in wall thickness, often visible through metallurgical inspection or thickness gauging. Corrosion products of general or uniform corrosion includes oxides and hydroxides, iron oxides, Fe2O3, Fe3O4, iron hydroxides, or other metal oxides depending on the material. Scale formation. A uniform layer of corrosion scale may form, which can sometimes be protective but often indicates ongoing corrosion. Implications of general or uniform corrosion includes, usually indicates a steady-state corrosion process, less immediate threat of catastrophic failure if detected early, but continuous loss can weaken the structure over time. Appearance and morphology of amine corrosion. Number 2 is localized corrosion morphology. Description: pitting, crevice, or filamentous attack confined to small areas, exhibits distinctive, irregular features that differ markedly from uniform corrosion. Number of the localized corrosion morphology is pitting corrosion. Visual features of pitting corrosion includes small, deep holes or cavities on the metal surface, often less than a millimeter in diameter, rough or jagged edges around the pits, corrosion products inside pits, dark deposits, rust or corrosion salts. Morphology of pitting corrosion includes deep, narrow cavities that penetrate into the metal. Pits may be circular or irregular in shape. Implications of pitting corrosion includes, pitting can rapidly compromise the structural integrity due to high localized stress and stress concentration, often difficult to detect visually until advanced inspection. Number B of the localized corrosion morphology is crevice corrosion. Visual features of crevice corrosion includes localized attack within crevices, welds, gaskets, supports or deposit zones, coloration, rust or corrosion products accumulating within crevices, corrosion deposits, often dark, flaky, or crusty deposits. Morphology of crevice corrosion includes localized thinning or corrosion at the crevice opening, degradation of material at the interface. Implications of crevice corrosion includes, can lead to sudden failure in confined areas, often associated with microenvironmental changes like acidification inside crevices. Number B of the localized corrosion morphology is filamentous or branching corrosion. Visual features of filamentous or branching corrosion includes corrosion filaments or hair-like structures extending from the surface, often observed in stagnant zones or areas with deposit buildup. Implications of filamentous or branching corrosion includes thread-like or filamentous growths composed of corrosion products. Appearance and morphology of amine corrosion. Number 3 is corrosion products and their morphology includes rust and oxides, usually flaky, powdery, or crusty deposits, sulfides or salts. In H2S containing environments, dark sulfide deposits can form, often in crevices or pits. Scale layers can be porous or compact, affecting the protective nature. Appearance and morphology of amine corrosion. Number 4 is indicators of corrosion severity, includes surface roughness. Increased roughness indicates ongoing corrosion, coloration, reddish-brown, iron oxides, black, sulfides, or greenish, copper salts. Presence of deposits, accumulation of corrosion products inside pits or crevices, material loss, thinning or perforation observed in severe cases. The appearance of corrosion provides vital clues for diagnosing the type and severity of damage. Regular visual inspection, combined with surface analysis, helps in early detection and mitigation of amine-related corrosion issues. Amine corrosion prevention and mitigation based on API 571. Number A, proper operation of the amine system is the most effective way to control corrosion, with particular attention to acid-gas loading levels. In addition, to avoid corrosive amine degradation products, the process temperature should not exceed recommended limits. Proper control of the reboiler rate and temperature is necessary in order to maintain a regenerator top temperature. Number B, proper attention should be given to avoid the buildup of SAW to unacceptable levels. Number C, the system design should incorporate measures to control local pressure drop to minimize flashing. In areas where it is unavoidable, upgrading to 300 series SS or other corrosion-resistant alloys may be required. SS410 trays and internals are also used in absorber and stripping towers. Number D, oxygen in-leakage causes high corrosion rates and contributes to heat-stable salt formation. Storage tanks and surge vessels should be blanketed with inert gas. Number E, solids and hydrocarbons should be removed from the amine solution by filtration and through process control. Filtration of rich amine solutions has the potential to be more effective than lean amine filtration for solids removal. Number F, corrosion inhibitors may be required to control amine corrosion within acceptable levels. Here's a comprehensive and detailed explanation of the prevention and mitigation strategies for amine corrosion, addressing both general, uniform, and localized corrosion. Introduction. Effective prevention and mitigation of amine corrosion are critical to ensuring the integrity, safety, and efficiency of gas treatment systems. The strategies involve a combination of material selection, operational controls, chemical treatments, and maintenance practices designed to minimize both general and localized corrosion. Prevention and mitigation of amine corrosion includes, number 1 is material selection, includes, number A, use corrosion-resistant alloys. Stainless steels such as 316L, 317L, offer better resistance against localized corrosion. High alloy steels such as duplex, super duplex enhanced resistance to pitting and crevice corrosion. Nickel alloys such as Inconel, Monel, excellent resistance, especially in highly aggressive environments. Material selection. Number B, coatings and linings. Application of protective coatings such as epoxy, polymer linings to internal surfaces, use of ceramic or rubber linings in particularly vulnerable areas. Prevention and mitigation of amine corrosion. Number 2 is chemical control, includes, number A, amine solution management, includes, maintain proper amine concentration. Excess amine can promote corrosion. Ensure pH control. Slightly alkaline conditions, pH greater than 8.5, help suppress acid formation. Chemical control. Number B is corrosion inhibitors, includes, amine-compatible inhibitors, such as film-forming amines, neutralizing amines, are added to form protective films on metal surfaces. Regular dosing based on system conditions and corrosion monitoring. Chemical control. Number C is oxygen and sulfide control, includes, remove or limit oxygen ingress to prevent oxidative corrosion, control H2S levels to prevent sulfide-induced localized attack. Chemical control. Number D is use of scavengers. Incorporate corrosion scavengers to neutralize corrosive species. Prevention and mitigation of amine corrosion. Number 3 is operational strategies, includes, number A, temperature control, includes, operate within temperature ranges that minimize corrosion rates, avoid high temperature zones where corrosion accelerates. Operational strategies. Number B is flow management, maintain adequate flow velocity to prevent stagnation, which promotes localized corrosion. Avoid areas with dead zones or low flow. Operational strategies. Number C is regular monitoring, use corrosion coupons, pH meters, and sensors to track corrosion indicators, conduct periodic inspection for early detection of corrosion damage. Prevention and mitigation of amine corrosion. Number 4 is design considerations, includes, number A, proper equipment design, includes, minimize crevices, dead legs, and welds where corrosive microenvironments can develop, ensure smooth internal surfaces to reduce deposit formation. Design considerations. Number B is drainage and cleaning, includes, design for easy drainage to prevent liquid stagnation. Schedule regular cleaning to remove deposits that can harbor corrosive agents. Prevention and mitigation of amine corrosion. Number 5 is corrosion inhibition and additives, includes, number A, film-forming amine additives, use of specialized amines that form protective films, reducing metal exposure. Corrosion inhibition and additives. Number B is pH buffers, addition of buffers to maintain stable pH levels. Corrosion inhibition and additives. Number C is inhibitor compatibility, select inhibitors compatible with system chemistry to prevent adverse reactions. Prevention and mitigation of amine corrosion. Number 6 is maintenance and inspection, includes, number A, routine inspection, visual inspections, ultrasonic thickness measurements, and corrosion coupons. Maintenance and inspection. Number B is timely repairs, weld repairs, relining, or replacement of severely corroded parts. Maintenance and inspection. Number C is deposits removal, mechanical or chemical cleaning to remove deposits that promote localized corrosion. Prevention and mitigation of amine corrosion. Number 7 is advanced and innovative approaches, includes, number A, cathodic protection, applying sacrificial anodes or impressed current systems in large storage tanks or buried piping. Advanced and innovative approaches. Number B is corrosion monitoring technologies, use of corrosion probes, fiber optic sensors, and online monitoring systems for real-time data. The key to effective prevention is an integrated approach combining material choice, chemical treatment, operational discipline, and maintenance. Localized corrosion is often more dangerous due to its rapid progression, thus, targeted strategies like inhibitors and design modifications are crucial. Continuous monitoring and proactive maintenance are essential for long-term system integrity. Amine corrosion inspection and monitoring based on API 571, number A, visual examination and UT thickness measurement are the methods used for internal equipment inspection. UT scans or profile radiography are used for external inspection. Number B, corrosion monitoring can also be achieved with corrosion coupons and/or corrosion probes. Number C, monitoring should target the hot areas of a unit such as the reboiler feed and return line, the hot lean/rich amine piping, and the stripper overhead condenser piping. Number D, fouling of exchangers and filters can be a sign of corrosion problems on the unit. Here's a detailed explanation of the inspection and monitoring methods used to detect both general, uniform, and localized amine corrosion. Introduction: effective detection of corrosion, both uniform and localized, is essential for maintaining the integrity of amine systems. These methods range from visual inspections to advanced sensor technologies, and they help identify early signs of corrosion, enabling timely intervention. Inspection and monitoring methods for detecting amine corrosion. Number 1 is visual inspection. This is purposed to detect surface deterioration, corrosion products, deposits, and physical damage. The application of visual inspection are including regular on-site inspections of equipment, piping, and vessels. Look for discoloration, rust, pitting, or deposit buildup. Use magnifying lenses or borescopes for detailed examination of hard-to-reach areas. The limitation of visual inspection is, it may not detect subsurface or microscopic corrosion, limited in identifying early-stage corrosion before surface signs appear. Inspection and monitoring methods. Number 2 is ultrasonic testing or UT. It is purposed to quantify metal wall thickness and detect uniform thinning or localized loss. Ultrasonic testing method uses ultrasonic transducers to measure the remaining thickness of pipes, vessels, or components, conduct measurements at multiple points to identify areas of significant loss. The application of ultrasonic testing are including, detect general corrosion through overall wall thinning, identify localized corrosion by measuring areas with unexpected or uneven thinning. The advanced technique of ultrasonic testing are including this method is a non-destructive testing, precise and quantitative. Inspection and monitoring methods. Number 3 is corrosion coupons and test pieces. It is purposed to assess corrosion rate and type over time. Corrosion coupons and test pieces method is installing removable metal coupons made of the same material as the system. Periodically retrieve and analyze the coupons for weight loss, pitting, or deposit accumulation. The application of corrosion coupons and test pieces are including, measure average corrosion rates, detect localized attacks such as pitting or crevice corrosion. The advanced technique of corrosion coupons and test pieces are including this method provides data only at specific monitoring points. Not real-time, requires periodic retrieval. Inspection and monitoring methods. Number 4 is remote and in-situ sensors, includes, number A, corrosion probes and coupons with data logging, includes, equipped with sensors to measure parameters like corrosion potential, linear polarization resistance, LPR, or electrical resistance, provide continuous or periodic data on corrosion activity. Remote and in-situ sensors. Number B is electrochemical techniques, includes, the first is linear polarization resistance, measures the electrochemical resistance of the metal surface, lower resistance indicates higher corrosion rates. The second is electrochemical noise, monitors fluctuations in electrochemical signals to detect localized corrosion onset. Remote and in-situ sensors. Number C is fiber optic sensors, measure parameters like temperature, pH, or corrosion potential in real time, useful for early detection of localized corrosion hotspots. Inspection and monitoring methods. Number 5 is corrosion mapping and surface analysis, includes, number A, scanning electron microscopy, provides high-resolution images of corrosion morphology, detects micropitting or initiation sites of localized corrosion. Number B, energy dispersive X-ray spectroscopy, analyzes corrosion products and deposits. Number C, surface profilometry, measures surface roughness and detects pitting or erosion. Inspection and monitoring methods. Number 6 is chemical and microbiological sampling, includes, water and deposit analysis, detects corrosive species, such as chlorides, sulfides, or oxygen, that promote corrosion. Microbiological sampling, identifies bacteria that could induce microbiologically influenced corrosion, mic. Inspection and monitoring methods. Number 7 is advanced and innovative monitoring techniques, includes, number A, acoustic emission monitoring. It detects sound waves emitted by crack propagation or localized corrosion activity. Number B, magnetic flux leakage. It detects wall thinning or pitting in ferromagnetic materials. Number C, laser-induced breakdown spectroscopy. It analyzes corrosion products in situ. Inspection and monitoring methods. Number 8 is inspection frequency and strategy, includes, routine inspections, visual and ultrasonic testing at scheduled intervals, continuous monitoring, deploy sensors for real-time data, targeted inspections, focus on high-risk areas such as welds, bends, or stagnant zones. A combination of methods provides the most comprehensive corrosion monitoring. Early detection of localized corrosion, like pitting, is critical to prevent sudden failures. Regular and systematic inspection programs, coupled with advanced sensors, enhance predictive maintenance and system reliability. Thank you.